Chapter number 7, the optimizer. Table and index access path. This lesson helps you to understand the execution plans that use operators related to table and index access methods. After you have completed this lesson, you should be able to describe the SQL operators for tables and indexes, list the possible access paths, and describe some common observations. In the first topic of this chapter, we're going to discuss what is a row source operation. A row source is a set of rows returned by a step in the execution plan. The row source can be a table, a view, or the result of a join or grouping operation. Row sources can be classified as unary operations, which are operations that act on only one input, such as an access path. They can be classified as binary operations, which are operations that act on two inputs, such as joins. And finally, they can also be classified as n-ary operations, which are operations that act on several inputs, such as a relational operator. The access paths that we're going to discuss within this chapter are ways in which a query retrieves rows from a row source. Examples of access paths are full table scans or an index scan. In the second topic of this chapter, we're going to have a brief overview of the main structures and access paths. A row in a table can be located and retrieved with one of the following methods mentioned in the slides. Now, in general, index access paths should be used for statements that retrieve a small subset of table rows, whereas full table scans are more efficient when accessing a large portion of a table. Now, whenever you're going to launch a query, the optimizer has to come up with an execution plan. Now, an execution plan that the optimizer always can take into consideration is the full table scan. Read all the records and filter out the records that are needed. However, whenever the optimizer sees that there are also indexes available, he's also going to take those indexes into consideration to see when they're going to be used, if it would lead to a much more efficient execution plan. So the optimizer is going to build up several alternative execution plans. Now, for each alternative execution plan, the optimizer is going to calculate a cost, and the execution plan that has the lowest cost will be the execution plan selected by the optimizer for the execution of that statement. All of the access paths that are mentioned in the slides are explained in much more detail in the subsequent slides of this chapter. The next topic of this chapter will discuss the table access path. During a full table scan, all the formatted blocks in the table that are under the high watermark are being scanned. Each block underneath the high watermark is only read one time. Now, first of all, the high watermark indicates the amount of used space or space that was formatted to receive data. Each row in each scan block is examined to determine whether it satisfies the statement's where clause by using the applicable filter conditions specified in the query. Now, because a full table scan reads all the formatted blocks in a table, it reads the blocks that are physically adjacent to each other. This means that performance benefits can be increased by using I/O calls that read multiple blocks at the same time. The size of such an I/O read call can range from a single block to any number of blocks up to the value of the parameter db file multi-block read count. So a full table scan will walk through all the records inside that table, and it can filter out the rows requested by that query. As you can see in the shown execution plan, there has been a full table scan performed upon table employees, And during the scanning of all the records inside that table, it filters out all the records where the last name equals king. Full table scans are faster than index range scans for large amounts of data. Now, whenever a full table scan is being used, you should ask yourself some questions. Are all full table scans being met? And also, at what percentage of data does the optimizer consider a full table scan as the most efficient way to retrieve the data from a table? Is that at 20%, 30%, 50% or higher? Now, when is a full table scan going to be used? Well, first of all, if there is no index available upon the table. If there is no index, the index cannot be used. So whenever you need to retrieve data from a table, it's going to be by default a full table scan. Also, whenever the optimizer calculates the selectivity, and the selectivity is low, that means a lot of data is estimated to be retrieved, a full table scan is probably going to be chosen. Also, whenever you request all the records of a table, he's never going to use an index. He says you're asking to retrieve all the records. I will do this by means of a full table scan. Also, whenever a query is being launched upon a small table, a full table scan is being used. Small table means that the table contains less than the DB file multiblock read count blocks under the high water mark. At that moment in time, a full table scan might be cheaper than an index range scan. Also, whenever you're going to use the hint full in your query, the optimizer is instructed to perform a full table scan. The row ID scan is an access method that is using the physical address of a record to locate the record inside the table. So the row ID of a row specifies the data file and the data block that contains the row and the location of that row in that block. Locating a row by specifying its row ID is the fastest way to retrieve a single row because the exact location of the row in the database is being specified. However, you rarely specify a row ID directly in a query. So in the first query on the slide, you see that I want to read a record from table employees, and via the row ID, I'm going to indicate where that record is physically located. And you can see that in the execution plan, that the table is being accessed via a row ID that is provided by a user. But like I've already mentioned, there is no way that you know all the row IDs by heart of the records in all of your tables inside your database. No, usually the database gets row IDs from an index scan of a table's index. So as you can see in the second execution plan being shown, you see that the table is being accessed, but via a row ID that is being provisioned by an index that exists upon that table employees. A sample table scan retrieves a random sample of data from a simple table or a complex select statement. This access path is used whenever in the statements from clause you include the sample clause or the sample block clause. Now, when you specify only the sample clause, the system will read a specified percentage of rows in the table and examines each of these rows to determine whether it satisfies the statement's where clause. If you would specify the sample block option as shown in the slide, the system will read a specified percentage of the table's blocks and examines each row in the sample blocks to determine whether it satisfies the statement's where clause. Optionally, you can add the seed clause to your sample or sample block option. Via the seed clause, you're going to instruct the database to attempt to return the same sample from one execution to the next. Plus also in your execution plan, you will see that the sample table scan has been used. Now there is one quiz concerning the table access paths. The quiz states that a full table scan sequentially reads every formatted block under the high water mark and filters out those rows that do not meet the selection criteria. Is this true or is this false? Well, this is true because indeed a full table scan will sequentially read every formatted block under the high water mark and will filter out those rows that meet the selection criteria. Or it filters out those rows that do not meet the selection criteria. An index is an optional database object that is logically and physically independent of the table data. Because they are independent structures, they require storage space. Just as the index of a book helps you to locate information fast, an Oracle database index provides a faster access path to table data. When you're going to create indexes, you can choose different types of indexes. You can use, for instance, B-tree indexes, which are the default type of indexes and the most commonly used ones. Similar in structure to a binary tree, B-tree indexes provide fast access by key to an individual row or range of rows. Keep in mind that the B in B-tree does not stand for binary, but rather for balanced. When you're going to create B-tree indexes, you can choose to create them as normal indexes, or function-based indexes, or reverse key indexes. You can even create index organized tables, which is a table that stores its row data inside an index-like structure. Also, when creating B-tree indexes, you can choose to create reverse key indexes, and you can also ask the B-tree index to store the index values in descending order. The default order is ascending. Next to the B-tree indexes, you can also create bitmap indexes. In a normal B-tree, there is a one-to-one relationship between an index entry and a row. That is, an index entry points to one single row. However, with bitmap indexes, a single index entry uses a bitmap to point to many rows simultaneously. You can also create application domain indexes, which are indexes that you build with packages and store those indexes either inside the database or outside the database. Now, the first type of index that we're going to discuss are the B-tree indexes. Now, each B-tree index has a root block as a starting point. Depending on the number of entries, there are multiple branch blocks that can have multiple leaf blocks. The leaf blocks contain all values of the column being indexed, plus the row IDs that point to the rows in the associated table segment. The leaf blocks are interleaved with each other. This means that previous and next block pointers connect the leaf blocks so that they can be traversed from left to right and vice versa. Now, the system can directly access rows after it has retrieved the address, the so-called row ID, from the index leaf blocks. So the index entry inside the leaf block of a B-tree index is composed of an index entry header. It will contain also the key column length and the key column value of the columns being indexed, as well as the row ID, the physical address where to find that record within the table segment. Now, a row can be retrieved by traversing the index using the indexed column values specified by the statement's where clause. Now, to perform an index scan, the system will search the index for the index column values accessed by the statement. Now, the index does not only contain the indexed value, but it will also contain the row IDs of the rows in the table that have that value. Now, there are several types of index scans that can happen when using B-tree indexes. Those types of index scans are discussed in the subsequent slides. An index unique scan returns at most a single row ID, and the optimizer will consider an index unique scan if the SQL statement contains a unique or a primary key constraint where clause, and also when all the columns of a unique B-tree index are specified with equality conditions. So if the customer ID is a primary key column, the optimizer will see this and he will state, yeah, there can only be maximum one time 9,999 inside that column. But that also means that there can only be one time 9,999 as a value in the index. So if he's going to use the index and he finds 9,999, he picks up the row ID and gets the record out of the table, but he doesn't have to scan any further the index because there can only be one 9,999 as an index value inside that index. This is the so-called index unique scan. The index range scan is a common operation for accessing selective data. Now, the optimizer will consider an index range scan when the optimizer finds one or more leading columns of an index specified in conditions and any combination of the preceding conditions. It will also consider using unique or non-unique indexes, and it will consider an index range scan if it can avoid sorting when index columns constitute the order by or group by clause and the index columns are not null because otherwise they are not being considered. Now, in the example in the slides, there is indicated that there is an index emp department IX upon column department ID. So the system, when the index is being used, will access the rows for which department ID equals 10. It will get their row IDs, fetches other columns from the emp table that is being accessed by the delivered row IDs by the index, and will finally apply any filters on those fetched rows to output the final results. Now, I've mentioned that whenever you're going to create a B-tree index upon a column, the column values will be indexed in the B-tree index, and those index entries will be sorted by default in ascending order. Now, whenever he performs an index range scan, this can happen in ascending order, but the index can also be scanned in the reverse order, in fact. So if you're going to, for instance, in your select statement, you're going to perform an order by clause upon the department ID column, and the department ID column has an index that is sorted in ascending order, but you ask to sort in descending order, well, it can walk through the index also in descending order, because with a sorted list, you can walk through it in ascending order, or you can walk through it in descending order. However, what you can do, you have the possibility to indicate when you create the index to have the values of department ID stored as index values in the index, but store them in descending order. If then the index is being used to perform an index range scan, it's going to be a descending index range scan, which is identical to an index range scan, except that the data will be returned in descending order. So although you say, I want to see all the department IDs lower than 30 in fact, the result, if the index is being used, will be returned in descending order because that index was created in descending order and will be accessed in descending order when the index is being used. You also have the possibility to create function-based indexes. Now, what you need to know is that if you're going to write a select statement with a filter that is using a function upon a column that is indexed, the index will never be used. Why is that? Because the optimizer, when calculating selectivity, when calculating cardinality, he does not know upfront what the outcome will be of, in this case, the function upper, in fact. So it says, look, if there is an index, I can never know for sure that using that index will be okay because I never know in advance the outcome of the upper function. Now, you have the possibility to create a function-based index like you see here. It creates an index upon table employees, but that will index the outcome of the upper function on the last name column. And the optimizer will consider using this function-based index when frequently executed SQL statements include transform columns or columns in expressions in a where or order by clause. So defining a function-based index on the transformed column or expression allows that data to be returned using that index, when that function or expression is of course used in the where clause or order by clause. But the column that is being indexed, and then that column is being used inside a function, the index will never be used unless it's a function-based index. Then you have the index full scan, and this type of scan can be used to eliminate a sort operation because data is ordered by an index key. So for instance, if you're going to carry out select star from employees order by employee ID, the result will actually be obtained via the index, in fact. An index full scan can be used to eliminate a sort operation because data is ordered by an index key. So let's suppose the following. You have your select statement upon table employees. You request all the records, but sorted upon employee ID. Suppose that the employee ID is indexed and that all the values in the employee ID column have an index entry within the index. Well, what it's going to do is, it says I can perform an index full scan because I have all the employee IDs inside the leaf blocks of my index. So I'm simply going to walk through all the leaf blocks default in descending order, pick up the row ID, and then with that row ID, I go to my table employees to get all the records out of that table in a sorted way. So the optimizer considers an index full scan when all the columns in the order by clause are in the index, or whenever the query requires a sort merge join, or a group by clause is present in the query and the columns in the group by clause are present inside the index. The index fast full scan is an alternative to full table scans when the index contains all the columns that are needed for the query. A fast full scan accesses the data in the index itself without having to access the table. So suppose the following, that you want to obtain the department IDs out of the table employees where department ID is not null. Now, first of all, in a couple of slides, we're going to see that null values are never being indexed. So if you have an index upon department ID and you look for the department IDs that are not null, he finds all the department IDs inside the index that are not null. And because you only want to retrieve the department IDs, you get all the department IDs out of your index, and there is no need to access table employees. This is what we call an index fast full scan. So this operation reads the entire index by using multi-block reads. A fast full scan is faster than a normal full index scan because it can use multi-block I/O just as a full table scan. Then the index skip scans improve index scans by skipping blocks that could never contain keys that match the filter column values. Now you have the possibility to create a composite index or a concatenated index. This means this is an index upon two or more columns. Now suppose that in table employees you have a column gender and you have a column age, and you have created a concatenated column index. That index skip scans improve index scans by skipping blocks that could never contain keys that match the filter column values. You have the possibility to create what we call a concatenated or a composite index. This is an index based upon two or more columns. Now let's suppose the following: you have a table employees that has a column gender and age, and you can decide on creating an index on the combination gender and age. What you will have is, to create the index, he will scan your entire table employees. He will then sort the records based upon gender. So first upon female and then upon masculine, because the F comes before the M. And then per gender, it's going to sort upon age, in fact. Now, your root block contains the distinct value upon gender, so female and masculine, and will also contain the minimum age value detected in a record that is female and the minimum age value that is detected for a row where the gender is masculine, in fact. And then what you will have is that the female entry will then be divided into leaf blocks, in fact, where you store ranges of age, in fact. So you have in this leaf block are the females with an age between 10 and 15. In that leaf block, females with an age between 16 and 19 and so forth. While this block here, that is the starting block for the masculine rows, in fact, you will have leaf blocks being created where they store masculines with an age between 10 and 15, masculine rows between 16 and 19, and so forth. An index skip scan improves index scans by skipping blocks that could never contain keys that match the filter column values. Then you have the possibility to create concatenated or so-called composite indexes. These are indexes built upon two or more columns. So we have here a table employees, and let's say that that table employees contains a column gender and age. And you can decide on creating an index on the combination gender and age. Now, in order to build the index, it will scan your entire table. It will sort the records first upon gender, and then per gender, it will be sorted upon age. Now, the root block of my index contains the two distinct values for gender that have been detected, female and male, and will also store the minimum age detected for female records and for male records. Then the index entry that points to female records will point me to this block in my index where I state the ranges that have been stored for the ages for the female records. And I have, for instance, the index entry F10 that points to the leaf block that stores the female records with an age range between 10 and 15. Leaf block number 2, which is pointed by F16 index entry stores the range female records between 16 and 19 SH and so forth. Those leaf index entries also contain then the respective row IDs. Same story for this block number 2, where it stores the male record ranges in fact. Well, this M10 index entry points to leaf block number 6, which stores the male records with an age range between 10 and 15, while leaf block number 7 stores male records with an age range between 16 and 19 and so forth in fact. Also, those leaf index entries will contain the respective row IDs. Now let's suppose the following that you're asking now. From my table employees, I would like to obtain the records where the age is between 20 and 29. Now it can consider a full table scan and do a filtering operation, but it can also consider using that index, although the index is not sorted first upon age. No, it's sorted upon gender and then per gender sorted upon age. But it can use that index in fact. Because he says, if I'm looking at my index, I have female and male records in fact. If I want to find female records with an age between 20 and 29, I have to go to this block in fact, and then I'm in my age range in fact, and I'm looking for an age between 20 and 29. Now he knows that he does not have to scan this leaf block because he sees this leaf block contains the age range starting from 10 till 16, so I do not have to scan this because it will never contain an age between 20 and 29. Same story, I do not have to scan leaf block number 2 because he sees that this leaf block entry points to this leaf block in fact, but that only contains from 16 till 20, so he doesn't have to scan this one. But he will have to scan leaf block F20 in fact, because there the age range is being stored from 20 till 25 in fact. I also have to scan the leaf block represented by F26 because there everything is stored from 26 till 29 in fact. But I do not have to scan the leaf block represented by this index entry because there the ages start from 30 in fact. So he only has to scan those two leaf blocks. And the same story for the male records, he only has to scan those two leaf blocks. So you have in total 10 leaf blocks, but only 4 of them need to be scanned to pick up the row IDs of those records where the age is between 20 and 29. The index join scan is a hash join of several indexes that together contain all the table columns that are referenced in the query in fact. So what do I have is I have an index upon the column last name, I have an index upon the salary, and then I'm asking, can you simply show me the last name and the salary out of table employees? Well, it says I have an index upon last name, I have an index upon salary. Well, I can simply join those two indexes together to give you back the last name and the salaries of the employees. Another example of the index skip scan is mentioned upon this slide. So it's assumed that there is a concatenated index or a composite index on the department ID and salary column. As you can see, when I'm querying my table employees, I only have a predicate upon the salary column and not upon the department ID column. So you might think we cannot use the index because the index is first sorted upon department ID and then per department ID it's sorted upon salary. Yeah, but he can still use that concatenated index, although you're not searching upon the leading column of this index in fact, because the skip scanning lets a composite index to be split logically into smaller sub-indexes in fact. The number of logical sub-indexes is determined by the number of distinct values in the initial column. So you have in your index, you have all the index values for department ID 10 and their salaries. Then you have a group of all the department IDs where it's equal to 20 and their salaries. So what he will do is you have smaller sub-indexes that are being created logically, and he scans the range of department ID, and from the moment in that range he sees a salary bigger than 15,000, he stops scanning that sub-index in fact, and he will jump to the next group, which is then department ID 20, and scans which department IDs are 20 with a salary smaller than 15,000. Once he sees a salary bigger than 15,000, he stops the scanning of that department ID 20 and he goes to the next department ID group. This is what we call an index skip scan. Now, I've already mentioned in one of the previous slides that null values of a column are never being indexed, in fact. So what does this mean is look, if I have here a table null test that is composed of two columns, a column 1 and a column 2, and column number 2 can never contain null values. That means that every record will have a value in column number 2, means that every value in column number 2 is being indexed as well, because it can never be null. While column number 1 can have null values. So records that have a null value in their column 1, and I would create an index upon that column 1, those null values will never be placed inside the index. This means that if I do a select statement and I want upon table null test and I want to find out all the values in column number 1 and I'm telling him to use the index, he cannot use the index because you're requesting all the values of column number 1, including the null values, but nulls never go into the index, so the index cannot be used. While if you're going to ask, for instance, select column number 1 from null testee where column 1 equals 10. Now when you have a predicate that always ignore null values, although column 1 can have nulls, the predicate ignore null values, so the index can be used in fact. If I would search all the values of column number 2 of my table null test, he can perform an index full scan because, like I've said, column 2 cannot have nulls, so all the values in column number 2 are being indexed. So single column B3 indexes do not store null values, and so indexes on nullable columns cannot be used to drive queries unless there is something that eliminates the null values from the query. So this is another example of keeping in mind that null values are never being indexed, in fact. So if you're going to create, let's say, a unique index upon column SSN of table person, know that that column SSN can accept null values, in fact. So if you're going to access that table, you want to find out the number of records, or you're going to access the column SSN, and you would search for nulls, in fact, it cannot use the index because the SSN column can contain nulls and nulls are never being indexed, in fact. However, you can say upon my column SSN, I'm going to create a primary key. This means that every record must have for its SSN column, it must have a value which is unique, but most important is that it must have a value, so it cannot be null. Well, at that moment in time, if you would say, I would like to find out how many records are in table person, I can simply do this by counting the number of index entries upon column SSN that was created due to the primary key definition, in fact. And I know that all the values of SSN are inside the index because it's a primary key, so it can never have nulls. Now, indexed organized tables is a structure to store data in an index-like structure. So the key values for the table as well as for the index are stored in one and the same segment. So To the application, it looks logically like a table, but underneath, the table data is stored in an index-like structure. Now, index-organized tables provide fast key-based access to table data for queries involving exact match and range searches. Changes to the table data result only in updating the index structure because it's using the index to store the table data. Also, storage requirements are reduced because key columns are not duplicated in the table and in the index. Here you have an example of the creation of a table of which you say that the organization must be indexed. So at that moment in time, the table becomes a logical concept, but to store its data, it's going to use an index structure. If then you're going to select from that index organized table where mno equals 9999, by the index structure, he can quickly locate where the record is with employee number 9999 and from the index returning that record. Yeah, these are the so-called index organized tables. In the previously discussed B-tree indexes, there is a one-to-one relationship between an index entry and a row. And an index entry points to a single row. But with bitmap indexes, a single index entry uses a bitmap to point to many rows simultaneously. If a bitmap index involves more than one column, there is a bitmap for every possible combination. Each bitmap header stores start and end row IDs. Based upon these values and the position of the bit inside the bitmap, the system uses an internal algorithm to map bitmaps onto row IDs. Bitmap indexes are widely used in data environments. These environments typically have large amounts of data and ad hoc queries, but no concurrent data manipulation language transactions. Because when locking a bitmap, you lock many rows in the table at the same time. For such applications, bitmap indexing provides reduced response time for large classes of ad hoc queries and reduced storage requirements compared to other indexing techniques. On the slide, they have created a bitmap index upon a table column. Now, when creating that bitmap index, Oracle is going to have a look at what are the distinct values within that column. And let's say for the example on the slide, the distinct values are blue, green, red, and yellow. In that bitmap index, it will also store the start and the end row ID that is theoretically possible inside the table. And then per key value, it's going to generate a bitmap. And if a bit is set to 1, it means that it represents that particular row. So the first bit in the blue bitmap is set to 1. And based upon the position of that bit and the start and the end row ID, it can calculate the actual row ID of that blue record inside that table. While the one over here, based upon its position and the start and the end row ID of the rows, in fact, he can calculate the row ID of that other blue record, which will point to that one. This is how internally a bitmap index looks like. Now you have here two examples on how a bitmap index access path is being used. So with the first select statement, you try to obtain all the records where country equals FR, and suppose that the country column has a bitmap index on it, in fact. Well, if the bitmap index is being used, he will locate the bitmap for FR, for France. He will look at which bits are set to 1, and based upon the position of that bit and the start and the end row ID, he's going to calculate the row IDs, and that's that so-called bitmap conversion to row IDs. And via those row IDs, we're going to access the rows within the corresponding table. In the other select statement, you're asking to show all the records where country is bigger than FR. Country has a bitmap index. Now this will result in a bitmap index range scan. So all the bitmaps where the key value is higher than in the alphabet to FR will be scanned. And based upon the position of bit 1 in each bitmap, he will calculate the row IDs, and via those row IDs, we're going to access the corresponding table. Now, bitmap indexes are also very effective for queries that contain multiple conditions in the where clause. Like for instance, this select statement says I would like to find out all the records where country is France or where the country is Deutschland. And we have a bitmap index on the country column. Well, he will obtain the bitmap of France out of the bitmap index. He will obtain the bitmap of Deutschland out of the bitmap index. And these two bitmaps are combined with the OR operator. That means if one of the two bits is 1, the result is 1. So the first bit for France is 0, for Deutschland it's also 0, so the result is 0. While the second bit for France is 0, but the second bit for Deutschland is 1, the result is 1. So this is your resulting bitmap, and then based upon the bit 1 inside the bitmap, he's going to calculate the row IDs. Same story, when you say, look, I have a bitmap index upon the country column, and I have a bitmap index upon the gender column, and you're looking for country France and gender male, he's going to search for the French bitmap in the bitmap index of country, that's this one for instance, and he will look up the bitmap for male in the bitmap index of the gender column, which is, for example, this bitmap. Now, because they are being combined with the AND operator, both bits must be 1 to result in a bit set to 1, in fact. So 0 and 1 with the AND operator results in 0. 0 and 1 results in 0. If it's 1 over here and 1 over there, this results in 1. And then, based upon the position of bit 1 in the resulting bitmap, he's going to calculate the row IDs. And via the calculated row IDs, we're going to access the rows in the respective table. So here you can see the two execution plans of the previously explained select statements, where you see, for instance, in that second select statement, we use the bitmap index for country, we use the bitmap index for gender, and those two bitmaps are then being combined with the bitmap AND operator, which results in a final bitmap, and then based upon the position of bit 1, it calculates the row IDs, and via the row IDs, we access the responding table. Now, on this slide, you will see a summary of all possible bitmap operations. You have bitmap conversion to row IDs, from row IDs, the count bitmap conversion. You have bitmap index single value, range scan, full scan. You have the bitmap merge, the bitmap AND OR, the bitmap. This slide summarizes all possible bitmap operations and their sub-operations. You have the bitmap operations, bitmap conversion, bitmap index, bitmap merge, bitmap AND OR, bitmap minus, and bitmap key iteration. For instance, if you take bitmap minus, what does this operation mean is that, let's say, if I go back to the previous slide, in fact, if you would ask, look, I would like to find out all the records where country is not France, well, he simply takes the bitmap of France and is actually going to reverse all the bits. So if you say not France, you take the bitmap of France and the zeros become 1 and the 1 becomes 0. So all the countries that are not in France, well, 0 becomes 1, 0 becomes 1, and the 1s becomes 0. And then the resulting bitmap will be used to calculate the row IDs, and this will give the row IDs of those records that are not France. This is what we call the bitmap minus operation. Then you also have the bitmap join index. Now, in addition to a bitmap index on a single table, you can create a bitmap join index. A bitmap join index is a bitmap index for the join of 2 or more tables. Such a bitmap join index is a space-efficient way of reducing the volume of data that must be joined by performing the join in advance. As you can see, when you create bitmap index, you see that in addition to a bitmap index on a single table, you can create a bitmap join index. A bitmap join index is a bitmap index for the join of 2 or more tables. A bitmap join index is a space-efficient way of reducing the volume of data that must be joined by performing the join in advance. As you can see on the slides, you have a table sales and customers, and your customers table holds a primary key that is referenced by a foreign key constraint defined inside the sales table. Now, in your create bitmap index statement, the from and the where clause allow the system to make the link between the two tables that represent the join condition between the two tables. Now, how does this bitmap index then looks like? Well, each entry or key in the index represents a possible city found in the customers table. A bitmap is then associated with each distinct city found in that customer's table. Each bit in the bitmap corresponds to one row in the sales table. In the first key in the slide, that's the key Ronje, the first rows in the sales table corresponds to a product sold to a Ronje customer, whereas the second bit is not a product sold to a Ronje customer. By storing the result of a join, the join can be avoided completely for SQL statements that are using that bitmap join index. A composite index is also referred to as a concatenated index because it concatenates column values together to form the index key value. You have the possibility to include up to 32 columns inside the index. Such composite indexes will provide improved selectivity if 2 or more columns or expressions are being used, and it will also give a reduced amount of I/O operation, because if all the columns selected by a query are in a composite index, the system can return these values from the index without having to access that table. So a composite index is mainly useful when you often have a where clause that references all or the leading portion of the columns in the index. If some keys are used in the where clause more frequently and you decide to create a composite index, be sure to create the index so that the more frequently selected keys constitute the leading portion to allow statements to use only these keys to use the index. An invisible index is an index that is ignored by the optimizer unless you explicitly set the parameter optimizer use invisible indexes to true, which can be set at the session or at the system level. So by default, when you're going to create an index is created as a visible index. That means that the optimizer can take that index into consideration to render the execution plan. And then of course, if you're going to update a table, like if you're going to insert a record into a table, a corresponding index entry has to be placed inside that visible index. However, you have the possibility to create or to alter an index to become invisible. That means that it's not seen by the optimizer. Now, what you can then do is, in your session, You can then set optimizer use invisible indexes parameter. You can put this to true. Then you tell the optimizer, look, there are invisible indexes for my session. When you're going to run your execution plan, you can take those invisible indexes into consideration. So you can test out if a newly created index, if it's worth having it in place. If it shows degradation of performance, you can then decide to drop that index. Now, one thing that you need to know is if you have an invisible index upon a table, and then you would, for instance, insert a record inside that table, also in the invisible index, the corresponding index entry needs to be inserted. So DML operations will be impacted by invisible indexes. Now here you can find the commands on how to create or alter an index to become visible or invisible. So if you have an existing index, index 1, and you make it invisible, and then via a hint you're going to tell the optimizer to use that index, he will simply ignore the hint because it says, I do not know about which index that you're talking because it has been made invisible. You can then, if you want to, make the index visible again. Now you can make an index immediately as an invisible index, but if you're going to create index, by default it is marked as visible. Now in the next couple of slides we have some guidelines for managing indexes and why or why not indexes will be used, or why not is going to use full table scans. Now some guidelines for managing indexes. It's well, create indexes after inserting table data. If you're about to insert 100,000 records, Oracle recommends to drop the indexes, insert those 100,000 records, and then recreate the indexes. Because if you leave the indexes in place while you do your bulk load of 100,000 records, this is going to impact the performance of that bulk load, because every time he inserts a record, the corresponding index entry also has to be inserted. Also make sure that you index the correct tables and columns. If you create concatenated columns, please think about the order of the index columns for performance reasons. Also do not index every column of each table because that consumes space and that will surely have an impact on the performance of insert, updates and delete statements. Also drop indexes that are no longer required. Also try to put your indexes in a separate table space, because indexes that are object that consume space, well, you can create, or you can ask the DBA to create a separate table space of which the space is only used for the storage of index information. If you're going to create very large indexes and to speed up the creation of those indexes, you can ask Oracle to create them with parallelism and even not to log the creation of those indexes. If you create indexes with no logging, the DBA actually should create all new backups. Also consider the costs and benefits of coalescing or rebuilding indexes, or before disabling and dropping constraints. Because if you have a primary key, an index will be created. If you drop the primary key constraint, it will automatically drop the index. If you then re-enable or recreate the primary key, that index has to be recreated as well, which can be, for very large indexes, can be a costly operation. Now you have the possibility to state, look, I would like to disable or drop my primary key constraint, but I want to keep the index in place. There is a small quiz. Assume that the column email has an index. Will the following query use the index upon the email column? So you say, look, I would like to obtain from the employees table all those people whose email address ends with the letter A. Well, because the wildcard search is in a leading position, so it's at the end, it will not result in a range scan, because an index, if you create it upon a characters column, it sorts alphabetically starting with the first characters. Yeah, it's not going to be sorted upon the last character, in fact. So it will not result in the utilization of an index range scan. Another quiz is asking how you can get optimum results from indexes. Is that by A, creating indexes before inserting table data? Is that B, to not order index columns? C, limit the number of indexes for each table? Or D, to not specify the table space for each index? Now, in order to get optimum results from indexes, try to limit the number of indexes for each table. In the next topic of this chapter, we're going to discuss some common observations. What do we mean with common observations? It's asking yourself questions: why is a full table scan used? Why is a full table scan not used? Or why is an index scan used or not used? Now, the first observation is, why is a full table scan used? Well, it can have some following common causes. You might have set parameters that affect the optimizer's cost estimation, and or a large volume of business data must be processed. That's whenever the optimizer calculates a low selectivity value. It means that the optimizer thinks that a vast amount of data is going to be retrieved. Why is a full table scan not being used? It can be that he's using an index full scan to avoid a sort operation, or that you have set parameters that influence the behavior of the optimizer, or the optimizer mode or optimizer hint is set to first rows or first rows n, or the query has a use nested loop hint that is not appropriate, or the query has a use nested loop first rows or first rows and hint that is favoring a nested loop join, or no parallel slaves are available for the query. Why is an index scan not being used? Because maybe functions are being applied upon the columns used in the where clause and you do not have a function-based index for it. There is a data type mismatch. If Oracle needs to do an implicit data type conversion, indexes cannot be used. Or maybe optimizer statistics are not available. He will then assume default values, or maybe the optimizer statistics no longer reflect the state of the data inside the table as well as in the index. Also, if the column can contain null, we have seen that nulls can never be indexed, in fact. So if the column can contain nulls, there might be a chance that he will not be using an index. Can also be that an index might be slower than not using it, or it's influenced by optimizer parameter settings, or the cost of a full table scan seems to be cheaper than a series of index range scans, or if there's simply no index available for the columns being used in your where clause, of course he cannot then use the index and he will go for the full table scan. Other reasons why the index scan is not being used: the available indexes are too unselective, the index cluster factor is too high. Now, the index clustering factor is something that is discussed in the chapter about the optimizer statistics. Or you have a query where you have used a hint that is preventing the utilization of indexes, or the index hint is simply being ignored, or certain parameters like the optimizer mode have not been set to their optimal value. Of Of course, if you perform a select statement with no where clauses, it's going to do always a full table scan, because with no where clauses, you ask to obtain all the records of a table. Now, one last topic of this chapter is about the automatic indexing task. Now, in Oracle Database 19c, the automatic indexing task has been introduced. Now, this automated task establishes a set of candidate indexes for creation during workloads in order to create single and composite indexes based upon single column usage or column group usage tracking. It will also validate the impact of indexes, but it can also look at which indexes should be rebuilt or should be disabled or should be dropped. It will also make decisions on whether to keep or drop the indexes, or monitor the usage of the indexes and drop the ones that are not used after a predefined and configurable time period. The benefits of this automatic indexing task is that actually your life becomes much easier, plus it also avoids that unnecessary indexes are being created by the developers. And if certain indexes are also being dropped, this can improve the performance of DML operations. Now, if you want to influence the interval to run this automatic indexing task, you're going to use the package dbms autotask admin. However, the automatic indexing task itself can be configured via the package dbms autoindex. And you can state, for instance, look, task, if you come up with a recommendation to create a new index and I would accept that recommendation, the index will be created, but I want that the automatic indexes being created are placed inside the table space IX. I do not want to get any recommendations on index creation, rebuild, or dropping of indexes for the schema HR. The configuration settings can be looked up via the data dictionary view DBA auto index configuration. Now, this slide shows the workflow of this new automatic indexing task. So what it will do is, in one of the first steps, it will identify the index candidates based upon column and column group utilization. He will then create indexes upon those columns that have been considered by the automatic indexing task, but he will create those indexes as unusable. This means that their definition exists, but it doesn't consume any storage space. Then in the third phase, the automatic indexing task will validate the auto indexes by compilation. It will use the top n past executed user statements to validate if the candidate indexes are worth being built or rebuilt. And this validation consists of two steps. Compile to check whether the optimizer would choose the new indexes, plus also execute to check the performance of SQL statements after rebuilding those indexes. If after validation at least one of the statements improves above some threshold, all the indexes rebuilt in the current iteration are marked as visible. If none of the statements improve significantly, they will be once again marked as unusable. In fact, statements that regress are being blacklisted to not use automatic indexes. An SQL patch is provided to not use these indexes. Also, the automatic indexing task will drop automatically created indexes that are not used for a long time. You can set this, for example, not being used for 53 weeks. Via the data dictionary view DBA indexes, you can review all the indexes that exist within the database and whether or not they have been created by this automatic indexing task or they have been created manually by developers and or database administrators. Now you have the possibility to ask for the generation of an automatic indexing task reporting. So what you can do is via the package dbms auto index, you have a function called report activity to get the result of auto indexing executions between the specified start and end time of the time period for which you would like to have that report. In that report, you can then see if the task created indexes or did it rebuild indexes, did it make them visible. So you can then look up via db alt index int actions, you can look up then those recommendations that you have called via that report activity function. You can also verify the performance on queries, updates, inserts and deletes that use these indexes. You can display all the new execution plans for queries that benefit from new automated indexes. You even have a hint to state to the optimizer, never take into consideration automatically created indexes. So I would like to find out what would be the execution plan if I do not have those automatically created indexes available, so that you can compare old and new execution plans that are using those new automated indexes. There are several data dictionary views at your disposal that provide information about different executions of the auto-indexing tasks and actions performed. You have DBA auto-index execution, where you can see the different execution of the auto-indexing task that runs periodically. You have DBA auto-index int action, which provides information about various actions performed on indexes. And in DBA auto-index SQL actions, you can see the various actions performed on SQL statements that have been verified by this auto-indexing task. Now in this chapter, you have learned to describe SQL operators for table and indexes, list possible access paths, and describe some common observations. Now the exercise of chapter number 7 cover the utilization of different access paths for better optimization. Workshop 7 of the SQL Tuning for Developers course. In this workshop, you will review the execution plan and several sections in an Event 10053 trace file, interpret information to understand the optimizer's decision, and learn how to use information in the 10053 file to tune an SQL statement. So you will review execution plans and several sections in an Event 10053 trace file, and you will interpret information to understand the optimizer's decision. Note that this workshop is only for demonstration purposes. So in my Event 10053 trace file that was captured for this select statement, I see that this execution plan has been used. Now, when looking at this execution plan, what is the total plan cost? Well, the total plan cost is in this case 962. And the total time estimate is 12 seconds. Now, where does this 12 seconds come from? Well, your 12 seconds is actually your plan cost, which is 962, multiplied by the single block read time, which we assume it's 12 milliseconds, using the same system statistics as we have seen in workshop number 6. So the meaning of cost 962 is that the optimizer computed that the preceding query should take as long as 962 single block reads. That cost equals an elapsed time of 12 seconds. Now in the event 10,053 trace files, you have a section that shows which parameters were being used by the optimizer. You can also examine if any altered parameter values influence the optimizer decisions. You can also compare 10,053 traces between two versions or two different execution plans to see why that plan is different. Then you have the section in that event 10,053 trace file concerning the base statistical information. Via that section, you can review if optimizer statistics have been gathered for each table and index referred by the query. Look especially for any tables that were not analyzed, because having no optimizer statistics will greatly influence the decision making of the optimizer, which will then perform dynamic sampling or assume certain defaults for selectivity and cardinality. Then you have the access path analysis section. You can determine in this section the path that correlates to the execution plan, and at the end of this section you can see the best single table access cost. So he says I have to access table sales. Well, I can do that by means of a full table scan and I will calculate the cost, or I can also obtain the information out of table sales that is needed by using the indexes that have been created upon that table sales. And the access path that shows the lowest cost, that is the access path that will be used for that particular table. Also, in the event 10,053 trace files, you have a section that will show you which join orders have been taken into consideration by the optimizer, and also evaluating for each join order the different join methods that are available, like nested loop, hash join, and sort merge joins. Now, they're asking here the question that if a user is complaining of slow response time of a query, you should then review the execution plan and the cost by using the explain plan and the plan_table table. Now let's assume that you look at the execution plan and that you see that the plan cost is 4,000. What is then the estimated elapsed time for the execution of that statement? Well, that is your plan cost, which is 4,000, multiplied by the single block read time, which we assume is 12 milliseconds. So your optimizer says, I estimate that this statement will finish in 48,000 milliseconds, but the user is complaining that it took 20 minutes to complete that query. So this means that the estimates that the optimizer has made are not done in an accurate way. Now, what could be the possible reason for an inaccurate cost? Can be because you have a large in list, large OR statement, a different estimated cardinality, or an incorrect selectivity estimates. Now, which statements are true regarding the hash joins? Well, only statement A is true, that system statistics can influence the optimizer's decision because hash joins require the intense use of memory and CPU. Hash joins are performed for equijoins, non-equijoins, and are most useful when joining large amount of data. That is not completely true. And hash joins can take advantage of the index on the join key column is also not true. Practices for lesson number 7, optimizer table and index access path. In the exercise of chapter number 7, you will examine the access path chosen by the optimizer for 12 different cases of table and index access. You find a listing of those 12 cases on this page. In this practice, you will explore various access paths that the optimizer can use, and you're going to compare them. You have the possibility of exploring 12 different cases, each of which is self-contained. All the scripts needed for this practice can be found in the access path directory. It is helpful to set the worksheet preferences to use access path directory as the default lookup path for the scripts. So to set the default lookup path to point to access paths, you're going to take your SQL developer, you go to Tools, you go to Preferences, Database, underneath Database, the Worksheet node, and make sure that you change the default path to look for scripts by SQL developer is pointing to the directory access path. Also, in your Files tab, you're going to click upon the refresh so that it shows that new lookup path access path. Now, the first case that you're going to look at is the case with and without an index. Now, the first thing that you will need to do is you will have to run a setup script file as the sys user, and that script file is going to grant the DBA role to SH. So SH is now a DBA, has all the privileges that it needs to perform the tasks that will be executed throughout the cases. So what you're going to do is you go to your SQL developer, you double click AP setup script file, make sure that you choose here the sys connection, and you're going to run the script. And what you see is session altered, grant has been succeeded, SH has received the DBA role. Then you're going to prepare the setup of your first case. And you're going to do this by running the index setup script file as user sh, which is going to create a table mySales, inserts data in it, gathers optimizer statistics for that schema sh, and is going to create an index called mySale prod ID IDX on the product ID column of the table mySales. So you go to your SQL developer, you look in the access path folder, you look for the IDX setup file, double click it, make sure that you choose here the SH connection, and you're going to run the script. It's going to insert quite some records inside that table mySales. And you wait until this script has finished. You can see the transcript of that script execution inside the activity guide. Now what we're going to do is we're now going to observe the execution plans that are generated by specific queries. And you're going to do this by launching queries in a worksheet that has a connection to the database as user sh. So we're going to open an SQL worksheet as user sh. That's the first thing that we're going to do. See that it's still running. So the index setup script file has now finished. So now we're going to open a worksheet as user sh. And then what you need to do is you're going to drop the index that was created on the prod ID column of the table mySales. You're going to execute this command to drop that index, and I say execute, and you see that the index has been dropped. Then what you're going to do is you're going to execute this select statement now inside that SQL worksheet. So I'm going to copy this and I'm going to paste it inside that worksheet. And what I'm going to do is I'm going to ask to auto trace this select statement. So execute it and also show me the execution plan. Now what do I see is that in order to obtain the result of this select statement, the optimizer says we're going to perform a full table scan, which is also the only method that it can use because there are no indexes upon that table my sales. So the only possibility for the optimizer is to use a full table scan to retrieve the records that are needed out of that table. But then what you're going to do is you're going to recreate that index upon that table my sales. And you can do that by running the script file create my sales index as user sh. So I go back to my SQL developer, going to say, look, I would like to it's create my sales. So this script file, I'm opening it, choose sh connection, and I'm going to run this script. He says, yeah, the index does not exist, but now he's busy creating that index. This will take some time. So the recreation of the index is now finished. So what I'm going to do now is go back to my worksheet as user sh, where I executed that select statement without having that index. And he chose a full table scan. And you can also see that it took 0.972 seconds to complete. But now my index exists and I'm going to re-execute that same statement. Now with the auto trace functionality, I'm going to say auto trace. And what do I see is that the optimizer sees now that there's an index available, takes it into consideration and decides that this is a much better way to carry out that select statement. And you also see that it only took 0.79 seconds to execute against the 0.972 seconds that it took to obtain the same result via a full table scan. Now this is already the end of the first case. And what you will need to do is you will have to clean up your environment by executing index cleanup script file. So I go back to my SQL developer, going to search for the script file index cleanup.sql, double click it, choose sh connection, and I'm going to ask to drop that table my sales. The second case is comparing single column index access. First of all, what you're going to do is in a terminal window, you're going to drop all the indexes that are currently created on the customers table by executing drop customers indexes script file. So let me show you this. So I have here a terminal where I logged in as user sh into pluggable database ORCL PDB, and I've executed this script to drop all the indexes on table customers except the primary key index. Once this is done, you're going to launch a query via the script file query00.sql that will force a full table scan. So what you're going to do is you go to your SQL developer, you open query00.sql by simply double clicking it, make sure that you choose the sh connection and you click upon the auto trace. And what you see is that a full table scan has been done and that the total cost of that full table scan is $410. 23. Then what you're going to do is you're going to create 3 B3 indexes on table customers. You're going to create indexes upon the columns cost gender, cost postal code, and cost credit limit. Now the index upon the customer gender, you're going to execute this by launching the script create cost gender index.sql. So I'm going to look up create cost gender index, double click it, choose sh connection, and I'm going to ask him to create the index. Then I'm going to create the index upon the customer postal code, in fact, by launching this particular script. So I look up create cost postal code index, double click it, choose the sh connection, and execute the create index statement. Then I'm going to create via this script an index upon the customer credit limit. So I'm going to look up customer credit limit index, double click it, sh connection, and execute that command to create that index. So now the 3 B3 indexes have been created. Then you can verify if the indexes really exist by executing list customers indexes.sql script file. So I go back to my SQL developer. I'm going to look up list customer indexes.sql, sh connection, and execute that statement. And I'm seeing that I have 4 indexes, but the 3 indexes created is the index upon the column customer postal code, customer credit limit, and the customer gender column. Then we're going to enable monitoring of those indexes upon table customers. You do that by launching the script file start monitoring indexes.sql. So I go to start monitoring indexes, sh connection, and execute this script. So I've enabled monitoring usage for all 4 indexes that exist upon that table customers. And then we're going to see if the indexes have already been used. Now I've just enabled the monitoring usage upon my 4 indexes. For all 4, it should state used equals no. So what I'm going to do is, let's say, show index utilization, open this, execute it as the sh user. And what I'm seeing is, I'm going to execute it like this. You see in the column use that all 4 indexes since the monitoring started have not yet been used. Then we're going to launch a script file that performs a select statement upon that table of customers, forcing him to use a certain index. So look, I'm going to go to query 01. So I'm going to open this, choose sh connection, and I'm going to do this auto tracing, in fact. Now what do I see is that an index has been used to carry out that select statement, and I'm seeing that the cost of using that index is less than the cost that I had when I have executed it without the indexes. So here my cost with the index is 218, while with the full table scan the cost was 423. So the optimizer has chosen to use only 1 index to do a full scan. The cost is lower than the full table scan. Then we're going to execute another query where we're going to ask to combine indexes together. And we're going to do that by launching the select statement inside the script query02.sql. So back in my SQL developer, look up query02, choose the SH connection and perform the auto tracing in fact. And what do I see is that he has used several indexes together in fact, and the utilization of all three indexes, the cost of it is much higher than when using only one index, but it is still lower than the full table scan that I had before. So this time the optimizer uses multiple indexes, combines them to access the table. The cost is higher than that from the previous steps, so when using only one index, but it is still lower than the full table scan. And then we can also have a look if those indexes have now been used because we have enabled the monitoring of the utilization of those indexes. So what I'm going to do is I go back to my show index usage.sql and I'm going to re-execute the select statement upon VDOLR object usage. Execute it, and you see now that all three indexes that they have been used since I have enabled the monitoring of the utilization. Case number 3 shows the utilization of the concatenated index. Now, first of all, in the previous case, you have created several indexes. Those indexes have to be dropped once again. So I'm going back to my terminal session. I'm still connected as user SH, and I'm going to re-execute this script to drop all the indexes except the index of the primary key. Then what you're going to do is you're going to run a script to create a concatenated index on the columns cost gender, cost credit limit, and cost postal code. You do this by launching the script create gender limit code index.sql. I'm going to look this up. And I have here the create gender limit code.sql. I open it and you see it's a concatenated index. It's an index on a combination of 3 columns. And I'm going to create this concatenated index as user sh. Then we're going to launch the script query01.sql that is going to carry out a select statement that has filters on all 3 columns that are included inside that concatenated index. I'm going to open my query01.sql. I open this, and what I'm going to do is going to auto trace this script or this select statement again, and you see that this concatenated index has been used. So the optimizer uses your concatenated index. The resulting cost is by far the best compared to the preceding steps. Then we're going to launch another select statement via query03.sql, and in that select statement we have removed the predicate, the where clause on the cost postal code. So it's almost the same as the SQL statement previously, but we have removed a filter. So I go to my SQL developer, I open query03.sql, going to choose SH connection, and I'm going to auto trace this, and it's still using this concatenated index. So although we have removed the predicate on cost postal code, the optimizer can still use the concatenated index. But the resulting cost is much bigger because neither cost credit limit nor the cost gender are very selective. See that cost is here quite high. Then we're going to execute another script, query04.sql, to carry out a select statement in which we have replaced the cost credit limit with the cost postal code, which has a much better selectivity, and if the index is being used, the resulting cost should also be better than compared with the previously executed select statement. So I go to my SQL developer, open query04.sql, choose the SH connection and do the auto tracing. It still uses the concatenated index, and I'm also seeing that the cost is far more or less than we had for that query 03 script file. Then we're going to launch another query via the script file query05.sql, where the leading part of the concatenated index is no longer part of the query. However, the optimizer will still be able to use the index by doing a so-called index skip scan. So I'm going to open this query 05, choose SH connection, do the auto tracing, and I still see that he's using the concatenated index and that he's performing a so-called index skip scan. In case number 4, we're going to observe the bitmap index access path. First of all, once again, we have to drop all the indexes that have been created upon my table customers except the primary key index. So I will go back to my terminal. I'm still connected as user SH, and I'm going to drop all the indexes except the primary key index. Then what we're going to do is we're going to create 3 different bitmap indexes on the columns cost gender, cost postal code and cost credit limit of my customers table. So first I'm going to create a bitmap index upon customer gender. So what I'm doing is I'm looking for create customer gender B index, bitmap index, open it, SH connection and execute this. And the bitmap index has been created. Then I'm going to create the index upon the customer postal code, the bitmap index. So here, create cost postal code B index, open it, choose SH connection, and execute the script to create that bitmap index. And then a third bitmap index that I'm going to create upon the customer credit limit. And that's over here, the create customer credit limit B index, bitmap index. Let me open it, go to SH connection and run the script. So now I've created the 3 bitmap indexes. And we're going to verify if all those indexes do exist in my database upon table customers. So I'm going to look up the script list customer indexes, SH connection, and I'm going to execute the query, and I'm seeing that I have 3 bitmap indexes that exist upon my table customers. Then we're going to auto trace the query in the script query02.sql. And we're going to see that the optimizer will only use 2 bitmap indexes to solve the query. However, the cost is not good. The cost is a little bit lower than the cost of the previously observed full table scan. So I'm taking my query02 script over here, choose SH connection and do the auto tracing. And he's using the bitmap index, but you see that the total cost is 416. Compared to the full table scan, it's only a little bit lower because at full table scan, its cost was about 425. In case number 5, we're going to have a look at the complex predicates with bitmap indexes. Once again, first of all, we have to drop all the previously created indexes. So I go back to my terminal session, still connected as user SH, and via running this script file, I'm dropping all previously created indexes except the primary key index. Then we're going to create 2 bitmap indexes upon the columns cost year of birth and the column cost credit limit of my table customers by launching the appropriate SQL script files. So first of all, the bitmap index on the year of birth. So what I'm going to do is I state create cost year of birth bitmap index, open this SH connection and create the bitmap index. And then I'm going to create the bitmap index upon the customer credit limit column. So I state here create customer credit limit B index, open it, it's SH connection, and I'm going to run that script again to recreate that bitmap index. Then we're going to auto trace the query in the script query 07 in fact. And what we will see is then that the query has a complex where clause that is well suited for using bitmap indexes. It will use the 2 bitmap indexes and the resulting cost is better than the full table scan cost. So I'm going to look up query 07. It's that one. SH connection, set auto trace. And I'm seeing that he's using the bitmap indexes that I've created upon customers, and I see that the total cost of combining those 2 bitmap indexes is a cost of 135, which is far more or less than the cost of 425 when deciding on performing a full table scan. Now the next question is about that we don't want that the optimizer no longer uses the bitmap index on the column customer year of birth. And we can do that by simply making that index invisible. And we can do that by executing the commands within this script file alter cost year of birth index. So let me show it to you. So here, alter cost year of birth index.sql, where the index will be made invisible, and then we're going to check if that index is indeed invisible. So I go to SH connection and I will run the script, and what I see is that that index upon the column year of birth upon my customers table has been made invisible. And then we're going to auto trace that query again in the script query07.sql. And what you will see is that the optimizer can no longer find a good plan that uses bitmap indexes. So now if I go back to my query07 and I'm going to auto trace this again, you see that the optimizer says, I think we're better off with a full table scan than by using that only one bitmap index that I am still seeing. In case number 6, we're going to investigate the index-only access path. Once again, first we will have to drop all the previously created indexes by running the appropriate script. So I'm going to run this script file again while connected as user HR, like this. And then what we're going to do is we're going to create a concatenated B3 index upon the columns customer last name and customer first name by launching the appropriate SQL script file. So what I'm going to do is I'm going to look up create last first name index. I open that. You see it's a concatenated B3 index upon last name and the first name column. Choose SH connection and run that script. And the B3 index has been made. And then we're going to auto trace the query in the script query 09. If I do so, if I look up query09.sql, SH connection, and I'm going to auto trace this, what do I see is that he can obtain my results without even having to go into the table, because the column information that I'm requesting is column data upon which that concatenated index has been built. So to obtain the last names and the first names, I do not even have to access the table. I can simply obtain the last name and the first name data by scanning the index itself. In case number 7, we're going to look at the index join. First of all, let's drop all the indexes that we have created previously by launching this script file. So now the previously created concatenated B3 index no longer exists. And then what we're going to do is we're going to create 2 separate B3 indexes, one upon the last name column and one upon the first name column. So it's not one concatenated index, but 2 separate indexes. We're going to do this by launching create last name index scripts and by launching the create first name index. So I'll go back to my SQL developer. I'm going to look up, so first the create last name index, open this, SH connection, execute it. So a B3 index on only one column, last name column, and also the script create first name index to create the B3 index upon the first name column, like this. Then what we're going to do is we're going to auto trace the query in the script query10.sql. So I'm going to go to query10 script. I open this, SH connection, and I'm going to perform this auto trace. And you see that he is using both B3 indexes. He doesn't have to go to the table to obtain last name and to obtain first name, because I found all the last names in the index upon last name, and I will find all the first names in the index created upon the first name column. But he will have to scan 2 separate indexes, and I'm seeing that that cost is much higher than the cost that I had in the previous case when we were using one concatenated index, because now 2 objects need to be scanned. In case number 8, we're going to observe the bitmap index only access. First of all, we will have to drop all the indexes that have been previously created by running this particular script file. And then what we're going to do is we're going to create one bitmap index upon the column cost credit limit by launching this particular script file. So I go to my SQL developer. I'm going to look up the create customer credit limit B index. I open this, SH connection, and I'm going to recreate this bitmap index. Then we're going to auto trace the query in the script query11.sql, which performs a select count star upon that table customers. And what we will see is that although the cost credit limit column is not a selective column, the count operation on its bitmap index is very efficient. So I take my query 11, I open this SH connection, I auto trace this. He's using the customer credit limit, and you see that the cost is 1. So this is really efficient for the count function. In case number 9, we're going to observe the B3 index only access. So we're going to, first of all, once again, drop the previously created indexes like this. And then we're going to create a B3 index upon customer credit limit. So not a bitmap index, but a B3 index. So I'm going to look up that script file, and I state here, create customer credit limit index. This will create a B3 index, not a bitmap index. SH connection. I'm going to execute this script. So now I have a B3 index instead of a bitmap index, and we're going to auto trace that same query again, stated in query 11.sql. So I go back, I take my query 11, I'm going to auto trace this. Now with the bitmap index, the count operation had a cost of 1, but if now I'm going to auto trace this, you see that he can use that B3 index, but the cost of using that index to perform the count is higher than when I had the bitmap index. So the B3 index in this case is less efficient compared to the corresponding bitmap index from the previous case. In case number 10, we're going to look at the function-based index. And of course, first of all, we're going to drop the indexes that we have created in the previous case, like this. Then we're going to create a B3 index upon customer last name by launching this script file. So I'm going to take here, create last name index. I'm going to execute this, and that B3 index upon customer last name column has been created. So there's an index upon customer last name. Now we're going to auto trace the query in query 12. And in that query, we're going to use a function to search in the column cost last name, the rows where I find gentle as a string. And we know that there is an index upon that column. So I'm taking my query 12, I open this, you see the function being used for the cost last name column, SH connection, going to auto trace. Now what do I see is that he's performing a full table scan. Now if you have a column that has an index, but that column is being used inside a function or an expression, it can never use that index, and it's going to be a full table scan. So although that there is an index, it cannot be used because its column is modified by that function. So how can you enhance the performance of this query that is using that function? That is by creating a function-based index. So what I'm going to do is, via the create lower cost last name index script, I'm going to build an index. That index is the result of the lower function of my customer last name column. I'm going to execute it. So now I have a function-based index that has been created. And then let's have a look at that query 12 script and see if now he can use that function-based index that I have created. So I go back to my query 12, going to auto trace this, and he can make use of this index that is built upon the result of the lower function upon my customer last name. Case number 11 is about the index organized table. Now, first of all, we will have to run the IoT setup script file as user sh to set up the environment for this case. So I'm going to look up the script IoT setup.sql, open this, choose sh connection, and I'm going to run the script, which is going to create a table called promotions IoT, which is an index organized table, and I'm going to then insert data into that index organized table. So I'm going to execute this script. So the table has been created, 500 rows have been inserted. Now we're going to auto trace the queries in script query 13a and query 13b. So first of all, I'm going to open both queries. I'm going to open query 13a and open query 13b. Now, first of all, we're going to auto trace query 13a, where we do a select statement upon that index organized table. I choose sh connection and I'm going to auto trace this. Now, what do I see is that the first query, so the one that I've just auto traced, lets the optimizer decide the plan, and the best is that it can find to perform a full table scan. Forcing the use of an index is not a good idea because it takes longer to execute. So you see that he chosen here a full table scan. This completed in 0.108 seconds. While if I auto trace this query, where I'm forcing him to use the index, if I auto trace this, you see here that it took 0.151 seconds. So it took longer. Now, they ask you to auto trace also the query in the script query 14.sql. Now what I'm going to do is over here, so query 14.sql, select star from promotions where promo ID is bigger than 300. I go to sh connection. I'm going to auto trace this, and what do I see is that the optimizer directly uses the index organized structure. You see sys IoT top 74173, which is extremely efficient in this case compared to the previous step, the statement that we have traced in query 13a and query 13b. We then have to clean up this case by running IoT cleanup script in order to drop that index organized table. And then the final case of this chapter is the so-called index skip scan. First of all, we will have to set it up by running the script iss_setup.sql as the user sh. So let us do this. So I have here iss setup, choose sh connection, which is going to create a table T with 2 columns and insert 10,000 records inside that table T, and then create a concatenated index upon column C and D of that table T. I'm going to execute this. So the table has been created, 10,000 records have been inserted, and the index has been created, which is a concatenated index. Then we need to auto trace the query in script query20.sql. I'm going to take that script file. I open this, sh connection, and then I'm going to auto trace this one. Now, what do I see is that the optimizer is not using the index and that it does a full table scan. Now, how can we improve the performance of a query, such as the one that we have just seen? Just to make sure that the right table statistics have been collected correctly so that the index skip scan can be used. So what you can do is via this script iss gather statistics, I can call upon the procedure gather table statistics of the package dbms stats to collect the latest optimizer statistics upon that table T. So I take sh connection, going to execute this, and the new table statistics have now been collected. And now I'm going to auto trace that query 20 script file again. So I take that query 20.sql and I'm going to auto trace this. The final case in this chapter is the index skip scan. First of all, we will have to perform a setup by running the ISS setup script file to set up the environment for this practice. So I go to my SQL developer. I'm going to look up ISS setup, open this, sh connection, and I'm going to run this script, which is going to create a table T with 2 columns, insert 10,000 records, and then create an index upon the combinations of column C and D of that table T. Then we're going to auto trace the query in the script query20.sql. I'm going to look up query20.sql, choose sh connection, and I'm seeing that he opts for a full table scan. So the optimizer is not using that index and performs a full table scan. Now, how can we improve the performance of that query, such as the one in the previous step? Well, for instance, make sure that the latest optimizer statistics are being collected, because a table was created, but at this moment in time there are no optimizer statistics yet. Well, there is a script file ISS gather statistics to collect table statistics upon table T of schema sh. I'm going to click here, ISS gather statistics, sh connection, execute it, and I'm seeing that optimized statistics upon table T have been collected. And then they ask me to auto trace again that query. And what you will see is, if now I go back to query 20, you see that the index is being used and that it performs an index skip scan and that the total cost is 2. But then you need to compare the result of the previously executed query with the query in the script query 21, where you want to force the select statement to perform an index fast full scan. So I'm taking my query 21, going to state sh connection, and you see that I'm forcing him to perform a fast full scan for that index, so it's using that same index, but the cost is much higher than the execution plan using the index of the previously auto-traced statement. And you simply have to run the ISS cleanup script file to clean up the environment for this final case. So here the ISS cleanup, open it, sh connection, which is simply going to drop that table T. This was the final case for this chapter number 7.